We are starting Chapter 5, Integration, but before we do, let me take a minute to refresh on a topic that we're going to see a lot, this idea of sigma notation. This is the capital Greek letter sigma, and it just means sum up between this starting number at the bottom to this top number up here, and this I is our variable, that is the thing changing from, in this case, 1 to 5. So if I were to sum up I from 1 to 5, what this means is take the first number, the first I, then add the next 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 I, all the way up to 5. Alright, and then one way to add this up quickly is take the n numbers and add them. That's 6. The next two n numbers, that's 6. So now we have 6 times 2, and then we're left with this last one, 3. So 12 plus 3 is going to be 15. One quick note is this I, it's irrelevant what letter we choose. Traditionally we choose I, K, N, sometimes J, but it's irrelevant. That can be anything. So all these, no matter what, because all of them are adding from 1 to 5, they're all going to add up to 15. So this is what we call sometimes a dummy variable. It doesn't matter what we pick. It's only there temporarily until we get what we're after. So in a case like this, where we get a little more interesting, it's not just summing up the k, we're summing up some function of k. So in this case, what we would do is we would say 2 times the first k, which is 0, plus 3 times the first k, which is 0, minus 1. And then, after that, now let's move k up 1. So 2 times 1 squared plus 3 times 1. Okay. Drew that parenthesis too soon. 3 times 1 minus 1, and then plus the last k, which is, since we're going up to 2, this will be the last one. 2 squared plus 3 times 2 minus 1. So because our sigma notation tells us to go from 0 to 2, I started off plugging 0 in, then I plugged 1 in, and then I plugged 2 in. And then we'd solve each of these. This one comes out to -1. Let me try to do this really quick. 2 plus 3 minus 1 is 4, and then this will be, 8 plus 6 is 14 minus 1 is 13, so this will be plus 13. So all in all, this should equal, am I getting 16? Okay, so that's a brief reintroduction probably to sigma notation. Now let me point out there's a couple shortcut formulas for things like this. So in other words, I wouldn't necessarily, if this went up to say 200 or this one up to 500, I don't actually want to write out the 1 plus 2 plus 3 plus 4 all the way out to 500. And luckily there are some shortcut formulas that have been developed. So let me get into those really quick. The first one is, if we're going from 1 to some fixed number n, and we're summing up some constant, then it's just that constant times whatever number we're adding up to. So for example, if we were summing up from, say, k equals 1 to 100, the number 37, so this is 37 plus 37 plus 37 plus 37 plus 37 plus 37, and we're doing it 100 times, and this is really just 37 times 100, or 3700. Alright, now in this one, if we're adding up from 1 to n of k, so whatever that dummy variable is, so this one, then we can just take that number that we're adding up to, multiply it times 1 more than itself, and then divide by 2. So for example, in that first one on the last page, we were going from 1 to 5, and we got 15, right? So that should work here. We plug in this number that we go up to into our formula, 5 times 5 plus 1 over 2, and sure enough, you get 30 over 2, which was 15. So now, if this number is really large, it's easy. We just plug it into this formula, n and n plus 1, multiply them together and divide by 2, and you get the sum of all the numbers from 1 to that really large number. If we're doing, instead of adding up k, we're adding up k squared, then we have this formula. So n times n plus 1 times 2n plus 1 all over 6. And then finally, if we were doing n to the third, or k to the third rather, and we're adding up to some really large number, so like, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, we can just stick the final number that we're going up to into here, n squared times n plus 1 squared, and divide by 4, and we'll get that summation. So it turns out, for our purposes, that's all we'll need, but there are other formulas for other powers of k. And for the more interesting formulas, we'll use some facts that come from this idea. So let's take a look and get into chapter 5 proper. So chapter 5 is all about integration. And chapter 5, or section 5.1, we're going to start out talking about the areas under curves. So we can, in general, find areas under straight lines. If we had something like this, and we'll see an example like this, let's say here's my axes, and I wanted to know, what is this area? Well, that's just a trapezoid if you look at it the right way, and so we know how to find the area of a trapezoid. You add up the bases and divide by 2, and then multiply times the height. So we'll do that in a second. But we're in a land in calculus where we're not always playing with nice straight lines. So we've got these curves, and we might want to know, all right, what's the area under this curve? And I'll give you a brief example at the end of the lesson on a practical reason you might want that related to distance and rate and time. All right, so if I wanted to find the area under this graph, x squared, well, you know what that looks like, but let me show you. This is the type of problem that we're going to try to solve. So the area under the graph here, let me get rid of my color. So I wanted to find the area under this graph between 0 and 1. And so that's just this area here. So we'll give you a preview of how we're going to do this. Put my coloring back in here. We're going to draw out some rectangles and calculate the areas of those, because we know how to find the area of rectangles. That's easy enough. But you can see what the problem with this is. If I've got, say, 3 rectangles, and I'm using those to estimate the area of this curve, I'm overestimating here, because if I calculate the area of these rectangles, this area above the curve shouldn't be counted. So this is an overestimation. I can switch that, and I'll be able to, we'll talk about, this is what you would call a right sum. I'll get more specific about that in a minute. But because the right end of our rectangles lands on our graph, I'm calling this a right sum. And then if I switch it, notice what happens. My left sum, so my left end of my rectangles, ends up on the graph. Now I'm underestimating the area on the graph. So I can do one of those, and just to be clear, it's not always that left will underestimate and right rectangle will overestimate. Depends on how your curve is going, but they're usually going to over or underestimate one way or the other. One other thing I can do is put more rectangles in there. So notice I've got 3 rectangles here, and I'm missing a bunch of space. But if I bring up half of this rectangle here, I can fill out some of that space. So for example, let me double the number of rectangles, and you can see that white space under there will kind of fill in. And if I want to be even more accurate, I can add some more rectangles on there. So the more rectangles you add, the better an estimation this is going to be. And then same thing with the right rectangles. So I started with 3, but notice as I add more rectangles, the area that I'm overestimating is getting smaller and smaller and smaller. So all these areas are smaller and smaller and smaller. All right, so let's look at how we're going to do this in practice. So our goal here is to estimate the area under curves. And the way we're going to do it is with this idea of partitions. So partitions are basically a set of x values. So the idea is, suppose we wanted to find the area under a curve between within some interval a to b. So if a to b is some closed interval, and we can break it up into n subintervals, so I've got a small interval here, small interval here, small interval here, and if you put these all together, you get the original a to b. So you've just broken it up. So a corresponds to the very first one, x naught, and b corresponds to the very last one, x sub n. Now, we're going to suppose that each of these subintervals has the same length. So we're going to call that length delta x. And the way you figure that out is you simply subtract the endpoints of the main interval and divide by the number of subintervals you have. So what we're calling a partition are those x values, the endpoints, x naught, x sub 1, x sub 2, all the way up to x sub n. So that set is what we call our partition of the interval AB. If we wanted to get to the kth value, so for example the third or the fifth value, then the way we do that is we say x sub k, which will be the kth value in that partition, that's the beginning times k of those delta x's. So that is, I want to go, say, 3 delta x's over. I start at the beginning, which is a, and I go over 1 delta x, 2 delta x, 3 delta x's. And that will get me to the third position, the third number in my partition. Okay, so that's the idea of a partition. Keep that in mind. Next, let's get to this idea of Riemann sums. Riemann sums are basically adding up, or let me say it this way, forming the rectangles that we were talking about earlier, where the f of x is the height of the rectangle, because that is what our rectangle, where our rectangle is landing on our function. So either the right side of the rectangle or the left side of the rectangle, one of those is going to be this f of x. And then the delta x, that's the width of our partition, but that's also going to be the width of our rectangle. So the left Riemann sum, this is like those left rectangles. The way you figure out what those xk's are start at the beginning of your partition, and instead of going k delta x's over, you're going to go k minus 1 delta x's. And if we were calculating the right Riemann sum, so the right rectangles, again, start at the beginning, but this time you're going to add k rectangles, k delta x's rather. Okay, so let's see how we use this. But this is what we call our Riemann sum. Right, I want to estimate the area under the curve of this function, 0.5x plus 1/2. Okay, let me calculate the left Riemann sum for this. So we want to estimate the area under this curve, 1/2 x plus 1, between the numbers 2 and 6, using 10 subintervals. So let me show you what this looks like first of all, then we'll get to the calculation. So we are calculating the left Riemann sum of this curve, the black line, which of course is just a straight line, using 10 subintervals. So we're using 10 rectangles to estimate. Now, clearly this is going to be an underestimation. Okay, let's do it. All right, so my function is, and I'm just gonna, I don't like decimals, so I'm just going to rewrite it as 1/2, and I want to calculate the left Riemann sum. So here's what we're gonna do. This is the Riemann sum, and I want to do this for 10 rectangles, so I go from 1 to 10. So if I'm gonna rewrite this, k equals 1 to 10, I want to plug in my x values into the function. So I have to figure out a is where I'm starting. A is the 2 at the beginning of our intervals. Delta x, then, the way we figure that out is I'm going to take the difference between the endpoints, 6 minus 2, and divide it by the number of subintervals, 10. So this is going to give me 2/5. So what that means is, in my partition, and we can figure this out, the first one in my partition is going to be 2, the second one will be 2 and 2/5. I won't do all of these, but just to get the pattern, 2 and 4/5. So each time I'm just adding delta x's. Let's do the fourth one, will be 3 and 1/5. And then what I should get is, all the way down to the bottom, x to the 10th. Now because we're doing left endpoints, this last one shouldn't be 6. It should be 1 delta x before 6. So 2/5 before 6 should get me down to 5 and 3/5. Because I want that left endpoint to be what hits the graph on my last rectangle. Okay, so what I'm plugging into my function, into x, is the x value that I'm calculating here. So that means my function will be 1/2 2, which is my a, plus k minus 1 times delta x, which is 2/5. And then that, keep in mind, that is just my function value. And actually, now that I look at it, I'm not quite done. I've still got the +1. So this is my function value, which should match everything here. Now I still have to multiply. So that's my f of x. I still have to multiply by my delta x, which is 2/5. Now let me pause here and just mention something about the notation you might be wondering about. We have this x star. And so what that stands for is the x that's in the kth partition that we're dealing with. What the star represents is the fact that we don't have to pick the endpoint, 2 and 2/5, 2 and 4/5. We really could pick any x within that subinterval, but for ease of calculation, we're just picking the endpoint, the left endpoint. All right, so now we've got our function, or our summation rather, set up. What I want to do is simplify this, because clearly this is not going to be pretty. Now anytime you have a constant being multiplied to everything in your summation, you can factor that out, because this is 2/5 times the first thing plus 2/5 times the second thing plus 2/5 times the third thing. So let's just factor that out. This is just basic arithmetic factoring. Okay, so what are we left with? Our summation, 2/5 times our summation, and I'm going to omit parentheses just with the assumption that everything after the summation now is related to that summation. K minus 1 2/5 plus 1. Alright, well, let me see if I can simplify even more. It would be nice if I just got rid of all these parentheses. Let me start that process. 2/5. Alright, so I'm going to factor in, or multiply in rather, the 1/2. So I've got a 1 plus 1/2. I'm going to move this 2/5 over. 2/5. K minus 1 plus 1. Alright, so clearly I can add the 1's together. I can cross those 2's off. So, and then I'm going to, I keep saying factor, and I'm going to distribute 1/5 in. I think this quarantine's getting to me. Alright, K equals 1 to 10. So let's see, what have I done here? I've got 2 plus 1/5 K minus 1/5, 1/5. And so I can simplify that a little bit further, just adding the 2 and the 1/5. So things are looking better. K equals 1 to 10. Let's see, that's going to be 10/5 minus 1/5 will be 9/5 plus 1/5 K. Alright, so for this next step, I'm going to be a little overly careful, but I'll skip this in the future. So what we can do with something like this, notice how we are adding 9/5 plus 1/5 K, and the summation tells us that we're adding all that together 10 times. So instead of adding these individually, let me add the 9/5 all together first, and then separately in a separate piece I'm going to add from 1 to 10 the 1/5 K. Alright, so in effect you could think of this summation as distributing into the summation within the parentheses here. Alright, and then this on the left, notice that's just a constant being added to itself 10 times. So this goes to that constant summation rule that we looked at earlier. 2/5 on the outside still, but on the inside we have 9/5 times 10, because we've added 9/5 to itself 10 times. And now in here we have a constant being multiplied times K. So we can factor that 1/5 out of all those K's being added together. And this is K equals 1 to 10 of K. Alright, and then instead of adding K plus K plus K, or rather 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, all the way up to 10, I'm going to use that formula that we looked at earlier. Okay, so what that leaves me with is 1/5 times, it was n times n plus 1 all over 2. That is adding K from 1 to 10. Alright, now it's just simple arithmetic. We can simplify this, that'll become a 2. Notice the 5 and the 2 down here multiply together and cancel with that 10. So this becomes 2/5 times, we have 18 plus 11, it looks like. And let's see, doing some quick math, that's going to be 2/5 times 29. Doesn't look like anything cancels with the 5 here, so we are stuck saying that this is going to be 58 over 5. which is, what, 17.4? No, that's not right. Let's, I think that's 11 point something. Yeah, of course, 55 is 11 and 3/5, so this must be 11.6. All right, and it turns out the actual area under this function, well, like I said, we could actually figure out what that was. So we can tell what that overestimation was. Let me go back to the graph and look at this. So we've got a trapezoid here. My base 1 is, well, this is up to 2. My base 2 is, looks like up to 4. And the height of my trapezoid, so I'm looking at this sideways, is going to be 4. So the actual area under this curve between 2 and 6 is, let me do that here, 1/2. We call it base 1 plus base 2 times the height. And that is 1/2. We had the first one going up to 2, the second one going up to 4, and then the height we said was 4. So this turns out to be 12. So, not too bad of an underestimation, but still an underestimation nonetheless. But that's okay. All we're doing right now is estimating. All right, let's look at a slightly different one, one that's a little more interesting with actual curves, and x to the third. So I'm going to go through that same process again. Notice in the last problem, I did skip the calculating the right Riemann sum, which would likely be an overestimation in this case, if the left Riemann sum was an underestimation. So in this case, I'll do the right Riemann sum, but feel free to pause the video and try this yourself first. All right, I'm gonna start this and then I'll speed through it, so you can hopefully pause it if you have a question about what to do, or what I'm doing rather. All right, so my function, let me write this on my paper here. Again, I'm gonna get rid of those decimals. All right, so the first thing I'm going to do is figure out what is a. Well, it tells me up here, I shouldn't skip over this. I'm between 0 and 1, so my a is 0, and my delta x then is 1 minus 0 over 3, so the endpoints subtracted over the number of intervals that I want, 3, and that is going to be 1/3. Alright, so I'm going to calculate the sum from 1 to 3 of f of x delta x. Now the delta x in my case is 1/3. It's a constant, so you'll always, in this class, you'll always be able to do this, but in a higher math class, so bring the 1/3 out, in a higher math class that won't necessarily be constant, so you won't necessarily be able to bring that delta x out. Alright, but here we can just plug in the x, and the x that we're getting, let me point that out, the x sub k rather, I should be a little more careful. The x sub k is a plus, and since this is a right Riemann sum, we're doing k times delta x, and so that is 0 plus k times 1/3, or let's call this 1/3 k. So now I'm plugging 1/3 k into f of x. So we are calculating 1/3 times the sum of k equals 1 to 3 of f of 1/3 k. Alright, so let's plug those in, 1/3 k's. It is going to be 1/2 times 1/3 k to the third minus 2 times 1/3 k squared plus 1/3 k plus 1.
Let's see, so let's get a common denominator here. Looks like 9 will do the trick, so that's going to be 6 minus 28 plus 18 plus 27 all over 9. Well, let's see, quick math here. 27 minus 28 is -1. 6 plus 18 is 24, minus the 1 is 23, so that gives us 1/3 times 23 over 9, so that's just going to be 23 over 27.
Now it turns out the actual area under this curve between 0 and 1, the actual area is 23 over 24. So our answer of 23 over 27 is a pretty good estimation. A little under, but pretty good. If we added more rectangles, so instead of going from 1 to 3, then we would probably get a better estimation. Not probably, we would get a better estimation. So 23 out of 27 is pretty good for only 3 rectangles. We will see in the very near future how to calculate the actual area, but for now let's just be satisfied with the estimation of the area under a curve. Alright, so that brings me back to the original question: how can we find the area under the graph of x squared? Well, at this point, again, I'm just going to say, just add more rectangles, and we can get closer and closer and closer. You can probably guess where I'm going with that, but I'll leave that for another time. Actually, the next lesson. So one place where this has some practical application is in the distance equals rate times time. And to be fair, this is still actually a fairly esoteric example, but it will give you an idea of maybe some application. So if we're driving at 70 miles an hour constantly, you drive for 1.5 hours, how far have you driven? Well, we know, given this formula, distance equals rate times time, that my distance will be 70, which is my rate, times my time, and being sure that the units match up, that's going to be 105 miles. But what's interesting is, another way to represent that, on a graph, if time is the x-axis and rate is your y-axis, that means if I didn't drive as fast, so if I only drove 60 miles an hour, it's the area of this rectangle, or in other words, the area under this curve between 0 and 1.5 that tells me my distance. So the area is represented by the curve. If I drive for a longer amount of time, I'm going to drive more distance. Or if I drive faster in that same amount of time, I'm going to drive more distance. So you're increasing the area of the rectangle either way. But what happens if I'm driving at a non-constant speed? So if I'm driving at 10x squared miles per hour, something that doesn't give me a straight line there. So it turns out the distance can still be figured out by the area under the curve. So again, time is on the x-axis, rate is on the y-axis. The area under this curve would tell me my distance that I've traveled. Okay, so stay tuned for the next lesson, section 5.2 in this book, where we'll figure out how to calculate the exact area under the curve.